Okay, today is our third lecture, and the topic of today's lecture is flat curve and the band curve. And that's our first topic. It's a flat curve. Assume a car moving with a constant velocity around a roundabout or a curve, and you have to find out the maximum speed the car can have and still turn safely. In the first step, you have to draw a diagram using all your imagination, in which you will include all the possible and unknown and unknown variables. Obviously, I'm talking about the forces, and then you have to draw a free body diagram. Okay, that's my imagination. On the left hand side, you will see a car um, moving on a flat curve, and the radius of the whole roundabout is r. And then I have converted this diagram into a free body diagram, and you will find out that there are obviously three forces. The one is the normal, the second one is the weight, and the third one is the force of friction. And you will see the direction of both as well. You will find out that the weight and the normal will oppose each other and might balance each other, and the force of friction is just directed toward the center of the circle. Now you have to analyze the situation, and you have uh, write down all the forces. First, the weight of a car, which is mg, the normal reaction as according to the third law of motion, which always oppose the weight, and the force of friction between the tire and the road, and it is the coefficient of static friction. Uh, Force of friction is trying hard to stick the car on the road. It is a uniform circular motion, means we suppose or we restrict the driver to move with a constant speed. Now here is the $1,000,000 question. Which force is acting a centripetal force? Now in the again going back to the previous diagram, the free body one, and you will again see that I draw a circle in the free body diagram, which is not included in the diagram. It is not a roundabout. Actually, just I want to mention that the force which is directed toward the center of the circle, working as a centripetal force, is actually the force of friction. Now we are going to derive the final expression for the maximum velocity. First of all, we use the equilibrium model for the y-axis. All the forces working along the y-axis sum up to a zero, and there are two forces, the normal and the weight, and the difference of these is equal to zero, which means normal is equal to mg, and there is a force of friction which is actually working as a centripetal force, which is always equal to mv square over r. When we substitute uh, the value of the normal here, and we'll find the maximum velocity a car can have will be equal to the under root mu, which is the coefficient of the static friction, and rg. Okay, hopefully done the flat curve. Now we are moving toward the bank curve. Consider an engineer have to design a road, a roundabout, in such a way that a car does not have to rely on the friction between the tire and the road, and it also have to prevent itself for skidding. To achieve his goal, an engineer must design a banker because it is not allowed to increase the radius of the roundabout, which can increase the velocity. The only thing he can do is to bank the curve. The first step, again the same. With all your imagination, you have to draw a diagram and then convert it into a free body diagram, including all the possible known and unknown variables. Now that's again my imagination. Think about a car moving on the bank curve, and the the banked road actually makes an angle theta with the horizontal. Now I have converted the whole diagram into a free body diagram in which the car will be denoted by a very big dot, a black dot. You can see that here, and the weight of the car is directed toward downward. Its normal is perpendicular to the surface, and which will makes an angle theta with the vertical. which is equal to the theta. You already solved in the theorems in the matrix as well. And this normal will resolve into two components. The component along the x-axis which is actually is vertical, and the component along y-axis which is actually uh, along the horizontal. You will see that the nx component, the normal component, is actually working against the weight. Now we have to analyze the situation. All the variables, weight of a car, mg, the normal, reaction n, and its components nx and ny. There is no force of friction, already suppose. So it's a frictionless surface. Because it is a uniform circular motion, so we restrict the driver to move with a constant speed. Again, the million-dollar question: which force is acting as a centripetal force? Okay, question is here: which force is acting as a centripetal force? What I have done here, I have just draw a circle just to make you understand that which force is acting as a centripetal force. It is clearly shown from the figure that the vertical component Ny is acting as a centripetal force which is directed toward the center of the circle. Moving for the final expression for the banking angle, uh, we have found that the vertical component of the normal is acting as a centripetal force. We apply the equilibrium model for the y-axis. All the forces working along the y-axis is equal to 0, which means n cos theta minus mg is equal to 0. Then we will develop and the horizontal component n cos theta will be equal to mg. Here n sin theta is working as a centripetal force will be equal to mv square over r. Dividing equation 2 by equation 1, and we will find the tan theta is equal to v square r g, and the theta, the banking angle, is equal to actually tan inverse v square over rg. And from here we can find out what angle, what is the banking angle for this equation. Now here is the painful part. You have to do some assignment. I have just given you some uh, a numerical, and you can solve easily. It is easy one. Consider three cars moving with three different velocities: 35 meter per second, 45 meter per second, 85 meter per second, moving around a roundabout which has a radius of 200 meter, and the coefficient of static friction between the tire and the road is 0.85. What you have to do? You have to find out which of these cars can turn safely. So there is an option, there is a possibility that might be some car may skid. And you have to also find out if you want to increase the velocity, the maximum velocity with this condition, extra 5 meter per second without increasing the radius of the roundabout, what we have to do? Obviously, we have to go for the bank curve. Okay, that is your assignment, and you have to do it, and you have to submit it as within 2 weeks. Now there is some different example known as the Ferris wheel. Consider a child of mass m rides on a Ferris wheel. The child moves in a vertical circle of radius r, moving with constant velocity v. You have to find out the force exerted by the seat on the child when it is at the top of the wheel and when it is at the bottom of the wheel. Now here is the step. Again, with all your imagination, you have to draw a diagram with all using all the possible and known and unknown variables, obviously forces, and then you have to convert the diagram into a free body diagram. Okay, that is my imagination. You have seen a Ferris wheel. Okay, don't worry about the diagram. You will find the concept here. So there are two conditions at the top and the bottom. The radius of the Ferris wheel is r, and the velocity by which the boy is moving on a seat is constant velocity v. Now we have converted into a free body diagram, and you will find there is only two forces, both on the top and the bottom. The one is the weight and the other one is the normal. Okay, now you have to analyze the situations. You have only two forces, weight and the normal. Normal at the top and normal at the bottom. It is a uniform circular motion. Again, We restrict the operator to move Ferris wheel with a constant speed. Now again the million dollar question, which force is acting as a centripetal force? Now get back to our diagram again, and again the question is still there, which is the force that is acting as a centripetal force. Now here is some difference between the previous example and this example is that the force which is actually acting as a centripetal force is not a single force, is actually the difference between the weight and the normal. So at the top and at the bottom, you know that for continuing a uniform circular motion, you must have a centripetal force, which means a force which is directed toward the center of the Ferris wheel. So here is the issue that at the bottom, uh, difference always results the normal force must be greater than the weight so that you have a centripetal force. In the same way, at the top, you must have a weight which must be greater than the normal so that you have a centripetal force. In both ways, you will continuously you have a uniform circular motion. Okay, what I have shown earlier, I have written down. The problem is different from previous problem. To understand it clearly, we must recall our previous concept that for the continuous circular motion, we must have a centripetal force. If this force is balanced, there is no more a circular motion. For this case, might be at the top and might be at the bottom, the difference of the two forces must result a centripetal force. So at the top, uh, the weight must be greater, and at the bottom, the normal must be greater, so that we still have a centripetal force. Here is the final expression for the force exerted by the seat when a child is at the top of the Ferris wheel. So as we have already understand that weight must be greater, so the summation of force which will result a centripetal force is equal to mg minus n normal at the top is equal to mv square over r. Then the normal at the top will be equal to mg minus mv square over, and we will have the normal equal to mg 1 minus v square over rg. Similarly, for the bottom case, here the difference is that the normal is greater than the weight, and the difference between the two forces will give you the centripetal force. So the normal at the top will be equal to mv square over r plus mg, and will take the common mg, and we will have 1 plus v square over rg. Now what will we do? The conclusion is that at the top of the Ferris wheel, the force exerted by the seat on the child is less than the true weight of the body, that is, child feels lighter. And at the bottom of the Ferris wheel, the force exerted by the seat on the child is greater than the true weight of the body, between child feels heavier. Again, the painful part, you have to do some assignment. I have written the whole numerical from the book, and you have to all of it you have to do 3 numericals, and using all your imagination and all you have understand here, and you have to submit the assignment within 2 weeks. That is your last numerical, and you will find the diagram as well, and you have to give some reason behind that. You have some values, but what you have to give me that why this situation is impossible. So think critical.